Hi everybody, welcome back to Chem 121. Sorry for the delay. Let's see here, what are we doing today? We're going to be working on gas laws some more. Which means that I need to have a web page open in a second, so let me get that ready. Lab worksheet number 3 is due tonight. Make sure you get that in by the deadline. Oh, that says quiz number 7. That's wrong. Hold on. That should say quiz number 6. We haven't put up quiz number 7. So, quiz number 6 is due on Tuesday the 24th. That's next week. And that closes on Wednesday. So make sure you get that one in too. Okay, so let's continue our discussion about air pressure. So at the end of the lecture yesterday, I drew a picture about how the weight of the atmosphere pushes down upon you based on your location. And if you are at sea level, wherever the sea is at the given moment, the amount of pressure that you would feel would be this amount here. And that checks out because how many atmospheres are above you? Well, it's the entire atmosphere, right? So we would call this 1 atmosphere pressure. In fact, that is the unit of pressure, is the atmosphere, or ATM. Now, the pressure that you feel changes day to day, and the reason for that is because of things like weather. Sometimes there is not entirely air above you, like, for instance, clouds. Clouds are made of water vapor, which have a different weight than oxygen and nitrogen do, and so they affect the pressure that you feel. Maybe you are sensitive to that and you feel like it in your joints or your ears or something, like you could feel the storm front coming in. But to visualize what our pressure looks like, so again, here's the ocean here, or the sea. And then here would be sea level, and then maybe we have a mountain over here and whatever. And then here's the atmosphere way up here. If you are at sea level, the pressure that you'd feel is equal to 1 atmosphere. If you are somewhere else, like, say, Denver. So here's Denver. There's a bunch of buildings here or something. I don't know. I'm just trying to make random pen strokes, and that ended up looking like a word. And I was like, ooh, that's kind of weird. If you're in Denver, then the pressure is much less than 1 ATM. Not much less, I should say. It's like 0.95 times atmospheric pressure. Because you are up higher than sea level. And so there's not as much air above you. And if you go flying in an airplane, there is even less air above you or around you. And so the effects of pressure are reduced. If you get all the way to the edge of the atmosphere, which is kilometers away from the surface, like very, 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 very far, then the pressure would be 0 atmospheres, and you would reach what we define as space, or a vacuum. And if you get to outer space, there's no air or any other particles out there. It's just a void. And the effects would be there'd be no pressure. So if you go out into space, like without a spacesuit or something to protect you, very bad things happen to you. And they are not necessarily only due to lack of oxygen. Like, you can't breathe in space. But, like, the instant that the airlock opened up and you were there, all of the air would burst out of your lungs. Because it would fill in the void. And then you wouldn't be able to inhale anything because there's no air to inhale. So you would suffocate as if your lungs were, like, in a state of constant, like, exhalation. Like, you're trying to force air out of you. You couldn't pull your air back in. It'd be awful. If you're in the sea, something similar happens, but it's because the weight of the water pushes all the air out of you, and you can't inhale because it's too much pressure. And those are both terrifying things. Let's not think about those anymore. A lovely way to start class. Here are 2 ways you can suffocate and die. due to extremely high or low pressure. Now, I didn't draw a picture for this, but you can envision that if there was a location that you could be that was lower than sea level, and there actually is one. If you've ever been to California, there's a place called Death Valley. It is a desert, surprising nobody, right? I mean, it's literally called Death Valley. The elevation there is like it's somewhere between -10 and -100 feet below sea level. And the atmospheric pressure that you'd feel there is just slightly higher. All right, mathematically, how do we represent pressure like in units that we understand or care about? So here are two units that we don't super care about, but they're common enough that I want to mention them. Of these two, we care about this one more. ATM is going to be the most important unit that we care about. And then PSI, and not so much. So this is for engineering. And then this is for blood pressure. So we're going to care about torr. The torr is also known as the millimeter of mercury. And so if you've ever measured somebody's blood pressure using like one of those old mercury columns where you squeeze the bulb and the little column of mercury goes up and then it falls slowly, and then as their heart beats it like wiggles, or I actually don't know how to read a blood pressure gauge. But I know mechanically how it works. The units of that are in torr. And so if you tell somebody that their blood pressure is, I mean, I'll just say what mine is. Mine's like 115 over like 71 or whatever. Those numbers represent millimeters of mercury. My blood pressure is like abnormally low, I've been told. And I don't know why, because I'm overweight. And I eat all the salt. And I go and I get my blood pressure and they're like, we have to take it again because that's too low to be safe. So I don't know what condition that is, but maybe I'm lucky or maybe I'm really not. Who knows? Somebody in chat will know though, right? The PSI is the pounds per square inch. This is mostly used for things like air pressure in your tires. So if you have a tire gauge and you put it in your tire and it says 38 PSI, what that means is that there are 38 pounds of force per square inch. And you can imagine a square inch is this little tiny area. That'd be like putting a weight with that size base that weighs 38 pounds on that square inch. So that's a lot of pressure. It's about 3 atmospheres. Like, that would hurt your ears. And for tires to be functional, we need a lot of air pressure in them so that they can push the tire against the road so that we get enough friction so that we can do things like, stop. We need friction to stop. We need friction to go. We need friction to do everything. So having enough air to do that is essential. Now, for these problems that involve pressure, you can convert back and forth between these. So just as a really brief exercise, what I want you to do is I want you to do the following problem here. And I'm going to put these conversions on the screen here. So this is just for practice because we're going to use these numbers a little bit. But what I want you to do is I want you to tell me what 497.2 millimeters of mercury. I want you to turn that into atmospheres, but I also want you to turn that into pounds per square inch. So I want you to do these conversions real quick, just as a proof of concept. I'll give you like 3 or 4 minutes to do it, and then we'll check the answers in a second. One more minute, we'll go over the answer. All right, so how do we convert these? Well, I gave you the conversions up there. And we just treat it like any other conversion we would do, right? So if I have millimeters mercury, which is the same as torr, and I want to turn this into atmospheres, in 1 atmosphere there are 760 millimeters of mercury. $497.2 over 760. All right, so there's my pressure in atmospheres. And then I can turn that into PSI by doing this. And so atmospheres would go down here, and pounds per square inch would go up here. Oops, I grabbed the wrong calculator. I grabbed the one on my desk. There we go. There you go. So that would be the pressure in those units. So depending on the application that we care about, you may need to convert from one unit to another. I don't think we'll ever see PSI again. But just for dimensional analysis practice, we can do that. All right. Let me know if you have any questions. All right. Now what we're going to do, now that we understand what pressure is, you already know what volume is because we've talked about that. You know what temperature is, and you know what counting is. So what we're going to do is we're going to control some variables. And I actually need to draw a picture for this, so let's put this back on the screen. All right. So let me scroll down here and we'll make a little diagram. All right. I have a balloon. And my balloon... Oh, I failed at my balloon. Hold on. So to get PSI, you'd use the conversion that I showed you for between PSI and ATM. All right, so here's my balloon. And in order for a balloon to be inflated, there must be gas particles inside of it, right? All right. Those gas particles are rebounding off the walls as they move around. Now, not all molecules hit the wall. They might go in any direction that they want to. But the collective feel of what the wall feels when molecules are hitting it is pressure. Now, there aren't just molecules on the outside of the balloon. There are also on the inside. There are also molecules on the outside of the balloon, right? So this would be the air outside, and this is in the balloon. And they're bouncing off the walls of the balloon as well. I'm going to give each of the samples of air a pressure. I'm going to have the pressure of the inside and the pressure of the outside. If the pressure of the air inside is the same as the pressure on the air outside, then what happens to the boundary of the balloon? Well, if they're being pushed on with the same amount of force, then nothing's going to happen to our boundary. The balloon's boundary will stay in place. But if the pressure of the inside was, say, greater than the outside pressure, so here's our boundary again, and here's our air. What would happen? So this is the inside and this is the outside. If this was the case, then the balloon would... What? What would the balloon do? Yeah, it could pop. So that would work. What I was going for was expand. We're going to assume that the balloon doesn't necessarily pop immediately as soon as we expand it. But the boundary would move, right? And as the boundary moves, the volume changes. So what we're going to do is we're going to look at the effect of P outside on the volume of the balloon. And the way that we're going to do that is we're going to put this balloon in a box, specifically a vacuum box. Here's our balloon. And our balloon has air in it, and that air is stuck in the balloon. There's also air outside the balloon. But what we're going to do is we're going to hook this up to a vacuum tube. And we're going to remove almost all of the air inside. What will happen to the balloon as I do this? All right. Hopefully you have a prediction because you're about to see this in action. So let me see if I can get this on the screen here. All right, it loaded first time, so that's a miracle. Boyles Law demonstration. That's what I want. So, and I need to get the bottom of the video here too. All right, so I'm going to mute this because I'm just going to talk over them here. Did I hit play? I did. Okay. There's our balloon. And we're going to turn the vacuum gauge on. And as we turn the vacuum on, all of the air is pulled out of the chamber and through this tube, so that less pressure is being pushed down onto the balloon from the outside. Now, the pressure inside the balloon remains whatever it does. And as we remove the air from the inside, the balloon gets bigger. Now we've released the valve and the air is flooding back into the chamber, which reduces the pressure. You can do this experiment with anything that has air in it. So this marshmallow peep, since it was just Easter and we have so many of these stupid things lying around, we're going to remove all the air from the outside. And it grows. It's alive! And then we'll put the air back in and it will be small. Alright. There's all sorts of things with air in it that you might not actually realize. This is shaving cream. And shaving cream is a very, very fine foam that is used to... I mean, you all know what shaving cream is for. But if you remove all of the air from the outside, all the bubbles in the foam expand, and then it grows, and then this happens. And then you're like, why did I do that? Now I have a mess to clean up. Alright, so what we observed there... I almost muted myself. I don't know why I hit that button. Is that There's my pen. All right, so we observed that as the pressure outside was reduced, the volume of the balloon increased. And we also observed that when we increased the pressure outside, the volume of the balloon went back to what it was, or in other words, it was reduced. And so these are opposites. So the effects are opposite, and so we call this an inverse relationship. All right. Now, mathematically, we can represent that as a formula. Oh, well, let me show you the formula real quick. Mathematically, the formula is represented by this. And what this means is that if I have some number, so whatever this ends up being, we'll just call this number x. If I change p, v has to also change so that I get x. So if I were to double p, so let's say that p1 equals 10 and v1 equals 5. So therefore, x would be 50, right? Because p times v equals x. If I double this, well, I'll call it v2, I guess. X still has to equal 50, right? So this number has to go down, and in fact, it goes down by the same factor. So the correct answer for this would be 2.5. So if I double one, I have to cut the other in half. If I triple one, I have to cut the other one by a third. And so on and so forth. They're proportional. One goes up by some factor, the other must go down by some factor, so that this statement is true. And we'll play around with this in a little bit. But let's talk a little bit about the more practical use of Boyles Law, which is, hey, you're going to inject people, right? This is what nurses train to do. They become proficient in syringes, and so whenever you're having a bad day, you can just stab somebody. No, don't actually do that. I hate needles, so I could totally see that somebody be like, yeah, this won't hurt, jab. Oh, I'm sorry, it hurt. All right. How do syringes work? Now, you'll notice that there's a headspace in this vial, right? So in this headspace, there are air particles. Or in some cases, depending on the medicine or stuff that's being used, there might be an inert gas, like, say, nitrogen or argon. That pressure inside there is exerting a force on the liquid. When you pull this plunger up here, there are very few air molecules in there because you've created a vacuum, right? And those air molecules would push against the liquid through the syringe. It's sort of the same situation as the balloon. Instead, in this case, we have water or a medicine or a liquid or something. Well, when you create a vacuum and there's very little pressure up here, there's more pressure on this side, so the liquid is pushed in this direction. But it has nowhere to go except up the syringe. And so the liquid will then slowly fill the syringe up until the pressures equalize. Now, as the volume of something changes, and like a certain area, it expands. So as this area in here, in this container, expands as the liquid is driven up the thing, the pressure of the gas decreases. Likewise over here, as this area gets smaller, the pressure increases. And eventually they will equilibrate to the same number. And when they do that, the liquid stops moving. All right. When we're using Boyle's Law, whenever you see a 1 and a 2, think of 1 as the before state and 2 as the after state. So on the screen here, I have a very simple problem, and I want you to try this before I go over the answer. Let's suppose I have a sealed syringe with 10 milliliters of air in it and 1 atm of pressure. And what I'm going to do is I'm going to expand the syringe to 20 milliliters. Now, the syringe is sealed, so it's not just going to pull in air from the outside. What is the pressure inside the syringe when you have pulled it to double the volume? So tell me the numerical value in atmospheres. Then we'll draw a picture and we'll see if you've actually done this experiment before as a kid. I don't know, because you had a syringe lying around? Maybe that got a little dark. I don't know. I'll tell you my farm story about that in a little bit. So first do this calculation. All right, one more minute. We'll go over the answer. All right, let's go over the answer here. Apparently somebody is mowing the lawn right outside my window, so hopefully that the mic doesn't pick that up. It's a pretty good microphone, but I chopped that a little bit too close there. There we go. All right, so let's write down Boyles Law. And so whenever I do a problem like this, what I like to do is I like to make a little grid to sort my information. So I can identify pressures and volumes by looking at the units. I can identify before and after by reading the problem and understanding, the context. So a sealed syringe has 10 milliliters of air inside it, which would be a volume, at 1 atmosphere of pressure. If the volume is changed to 20 milliliters, what would the pressure be inside the syringe? So we're going to solve for P2 because that's the box we didn't fill in. So let's do that. So P1 V1 over V2 equals P2. And then I'm just filling in all the numbers. And so that looked like that, and these units would cancel. And I would get half an atmosphere. Now, let's look at that from the perspective of our diagram that I'm going to draw. So here's my, oops, hold on, let me get rid of this dotted line. Here's my syringe. We've stoppered the end, and I have a movable piston that I can move. So 10.0 milliliters and then 20.0 milliliters. Oops. So with this state, I would have, here's all my gas inside. But if I were to move this back to over here, I have the same number of molecules, but they're just spread out over a larger space. So I'd go erase 3, 4, 6, 7, 8, 9. That's good enough. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. And you can see the same number of molecules over a larger space means that the molecules have more area to cover, and so there could be less collisions per area. And as a result, the pressure must go down. So as V increases, the pressure decreases. Because they are inversely related. So you can check your answer immediately and go, oh, I got a number that was bigger, but I increased the volume, so I must have made a mistake. Now, I don't know if you've ever played with like a syringe, but I grew up on a farm, and my parents did veterinary work for farm animals that we had on the farm. And so we would have like large syringes for medication around. And of course, as a child, when I'm running around in the barn and like getting into all sorts of stuff that I'm not supposed to, one of the things that I had found as a child was an empty syringe, like a really large one. And so I would play with like you put your thumb on the end and then you try and pull it, and then like it sucks itself back to where it was because of Boyles Law. If the pressure on the outside is not the same as the pressure on the inside, the syringe starts moving. So I realize now that I'm telling that story that that is not a normal childhood. They are not playing around with like medical supplies and like stuff like that. But I don't know, maybe you had a similar experience with, say, like, I don't know, a soda bottle, I guess, where you like try and breathe into it and expands or whatever. This analogy is just getting worse and worse the more I think about it, but anyway. All right. Let's do another experiment. What we're going to do this time is we're going to change the temperature inside. Why can't I? There we go. Get my cursor here. Let's draw a picture for this too real quick. This picture is going to be a lot simpler to draw. So I have a balloon, balloon, and I have particles inside it, and they're at some given T. I'm going to heat the balloon up. This is my heating element. And so my balloon now has molecules that are moving much more quickly. What happens to its volume? If I were to heat the balloon up, what would happen to its volume? Likewise, if I were to reduce the temperature, what would happen to the volume? Well, I hope you have an answer, because we're going to watch another video. Let me prepare the video. Where is my cursor? That's not what I wanted. Oh, I don't have a cursor. That's why. Oh, everything disappeared because I'm the worst. There we go. I'm aware my browser's up to date, YouTube, for fuck's sake. Hold on. Okay, now it's working. There we go. All right, so here's our balloon. Oh, it's good to know I'm not the only one who didn't have who had an unusual child. All right, I'm actually going to turn the audio on for this one because you can hear the balloon crackling. We're going to pour liquid nitrogen on this balloon. Liquid nitrogen is incredibly cold. It is minus 180 Celsius or so. I want to say. Yeah, I think that's right. It's like 90 Kelvin. All right. Here's what happens when we pour liquid nitrogen on the balloon, which will rapidly cool the air inside it. All right. What happened to the volume of the balloon? So very clearly, it kind of shrunk and got reduced in volume, right? So as I lowered its temperature, the volume was reduced. Now what we're going to do is we're going to let the balloon slowly warm back up to room temperature because it's a gas, and liquid nitrogen evaporates incredibly quickly. So once it just is all blown away, the balloon should warm back up to whatever ambient temperature is around it. What will happen to its volume as it does that? Well, let's see. Ta-da! It's alive! And it looks almost exactly the same as it did before. So what have we learned from this experiment? Well, we learned that if we reduce the temperature of our balloon... I'm in the wrong window on my screen. Hold on. If we reduce the temperature of the balloon, the volume also gets reduced. And as I allow something to warm back up, it increases the volume as well. So these are the same. So we call this a direct relationship. So temperature and volume are directly related. If you increase one by some proportion, you increase the other by the same proportion. So if you double the temperature of the air in the balloon, you also double its volume. So, can you be more specific on what you need to know? Let me put the volume temperature formula on the screen here. So it's hard for me to typeset fractions, but this is what this looks like. And we'll put this back on the screen. So these are both the same sort of circumstances before. You have a before and an after, and it's V and T. Now, the only issue that we have to run into here is that temperature has to be in Kelvin. So this is really important. Remember a long time ago when we talked about temperature that we had to use Kelvin and not Celsius, because if you input 0 Celsius, you divide by 0, and that'd be no good. So when the temperature goes up, the balloon gets bigger, because we said that these relationships were direct. When we pour the liquid nitrogen on it, it is freezing cold, and so the balloon shrunk. And then it warms up slowly as the nitrogen goes away. That was not boiling water, that was liquid nitrogen. Liquid nitrogen is freezing cold. All right, I'm going to give you an example here. So I want you to make another little chart and fill the numbers and then solve the equation for the variable that I want to know. A balloon with 1 liter volume is at room temperature, which is 298 Kelvin. What temperature does it have to be in order to have a volume of 1.5 liters? So we're going to increase its volume by like 50%. What must the temperature be? Now, you are solving for a temperature, which means you're going to be solving for something on the bottom of the equation. So be careful with your algebra, and we'll go over the answer in about 5 or so minutes. So see you in a bit. All right, one more minute. We'll go over the answers. All right, so let's go over here. I'll put the problem on the screen here. All right, so a balloon with volume 1 liter at room temperature 298 Kelvin. What temperature must it be to reach a volume of 1.50 liters? Okay, so I'm going to solve for T2. Now, I can't just have T2 on the bottom. It's got to be on the top. So I got to multiply both sides by T2 to cancel it out over there. So that gives me this. And so now I just have to undo everything that's over here. So I would say divide by V1 to cancel those out. And then multiply by T1 to cancel those out. And yes, you do have to do those steps for the algebra because otherwise you get the wrong answer. So the volume 2 was 1.50 liters. The temperature 1 was 298 Kelvin. And the volume initially was 1 liter. And so when I do that, I get 298 times 1.5 divided by 1. And there you go. So the temperature went up by some 150 degrees or so. All right. We're going to take a break real quick because we're at about that time. So let me put this clock on the screen. It has been very windy spring weather yesterday and today, so for the next song that we're going to put on for Stardew Valley, we're going to see if we can evoke some familiar memories of a breezy summer day. Alright, we're back. Turn this down. Alright, so we've seen how temperature and volume are related. We've also seen how pressure and volume are related. Now we're going to look at the last variable related to volume, which is number. And this experiment I can do on my own, although it's a little more effective if I do it in person. So I don't have a webcam, so I can't actually do that. But what I can do is I could draw this on the screen here. And I can say, well, once I scroll this all the way back up to the top here. Let's suppose I have a balloon. So here's my balloon. And it hasn't been inflated yet because I haven't put any air into it. So there's some amount of molecules in there. Now I'm going to add more molecules in there by inflating it. So I'm going to go... There we go. So I've added molecules to the balloon. What happened to its volume? Well, as the number of molecules increased, very clearly the volume increases, right? And if I were to reduce the number of molecules by letting air out of the balloon, that works better in person when I can do that quickly. The volume goes down. So, very clearly, the relationship between number and volume is a direct relationship. Now, there's not really a formula for this relationship, but it's going to become useful in a second when we talk about the ideal gas law. All right. Now, we can put the pressure, volume, and temperature laws together to get this. This is called the combined gas law, because we've combined Boyles and Charles' law, basically. And what this is used for is a circumstance where you have measured all of the variables and you want to figure out one by controlling the other two. So for instance, let's look at this type of problem here. A balloon with oxygen gas has a volume of 2.26 liters at 1 atmosphere and 298 K. Suppose that I move the balloon, and now the temperature is 265 K and the pressure is 0.835 atmospheres. What would the volume of the balloon be under these circumstances? So what I want you to do is I want you to make a chart just like we did before, except instead of having two variables in it, you'll just have three. So something like this. But otherwise, the setup is the same. Figure out which variable you want to solve for once you've filled in the chart, and then do the algebra. So go ahead and try this. I'll give you like 4 or 5 minutes to do it, and then we'll go over the answer. All right, 1 or 2 more minutes, and we'll go over the answers. All right, so I'm going to go back over to this screen here. And we'll make a new little chart. So let's see here. So PVT. 1 and 2. All right, so we've got a volume, and we've got a pressure, and we've got a temperature. And these are all our initial conditions. Then we're going to move the balloon to a new location with a new temperature and a new pressure. What is the volume of the balloon? There we go. So we could set up our equation. And we're going to solve for V2, which means that we're going to multiply both sides by T2. So let me just set that like that. So we'll move the T2 to the other side and then move the P2 to the bottom. So this goes up there and this goes down there, and then they cancel on this side. And then it's just a matter of filling in all the numbers. So V1 was 2.26. Oops, hold on. Don't forget your units. T2 was 265. Divided by T1, which was 298. And P2, which was 0.835. All right, so then we'll cancel out our units, make sure everything cancels except for the liters, which is what we should get. We'll punch it in the calculator. Now we're dividing, so parentheses, 298 times 0.835. Close the parentheses, enter. I get 2.41 liters. All right, excellent. So by moving the balloon to these conditions, the balloon expanded slightly. Despite the temperature going down, the pressure going down had more of an effect. So the balloon did get bigger for that reason. All right, I have one more video that I want to show you because it is sort of relevant. So what new location could this be where the temperature goes down, but also the pressure goes down? So let's see if I can find it really quickly. There we go, I found it. I don't know if you could hear that. Let me turn the volume up here. So I have this video. Now, I don't know what country did this. Oops. A little small in the corner there. So I have no idea what the nationality of the people that did this was. Some strange people that worship maple syrup or something. I don't know. All right. In the back of this, you could see right here, this is a weather balloon. And it's really big. And they're filling it with helium. And what this is going to do is the balloon is connected to a long cable that has a GoPro camera with our little Lego friend holding the Canadian flag. I'm Canadian, which is why I'm making all these stupid jokes. We're going to let the balloon go, and then we're going to watch what happens. Now, you unfortunately can't see the balloon, but what I can tell you about outer space is, one, there's no air pressure up there because we're going beyond the edge of the atmosphere, and two, very, very, very cold. So let's watch and see what happens here. All right, there he goes. We're in the clouds. Now we're above the clouds. Now we're really above the clouds. Now we're so high up that there's not even wind anymore. It's just quiet. There's the sun. Hi, sun. I think the moon makes an appearance in a second here. Yeah, there it is. So we're way up here. It's real high. How the heck did they get the video back? I mean, we have radio and stuff, like, just beam it to a satellite or whatever, right? Or there's a more practical reason. There's the moon again. Uh-oh. What happened there? You probably heard the big snap sound. What do you think happened to our balloon? And then once you've figured out what has happened to the balloon, why do you think that happened? Why would the balloon burst? Well, if we're going way, way up where there's very little pressure and very little temperature, the effective pressure is probably going to make the balloon so big that it eventually snaps. And then this happens. You get a hell of a view. And so the story is that apparently this fell like within a kilometer of where they launched it. And they were able to recover it because there was probably like a beacon or tracking device on it. And then they uploaded this to YouTube, where I then proceeded to show the video 3,741,000 times to students. So that's the weather balloon video that I like to show. So gas laws have a lot of practical applications that we're going to be seeing here and there in this class and also beyond. So, all right. The last bit of stuff that we have for gas laws is what's called the ideal gas law. And if you take Boyles Law, Charles' Law, and then also another law that relates number in there that we didn't talk about, you get this. So the ideal gas law relates PV, N, and T together using a constant. Now, how do you know when to use the ideal gas law? And the answer to that is when there is only one state in the problem. So you cannot do a before-after with the ideal gas law. It doesn't work. The ideal gas law does not support that. It allows you to solve for any variable given that you know the other three. Now, R is a constant, and R is equal to this number. 0.08206. In fact, it is known as the gas constant. Whenever we use gases, we use the gas constant. if we're using a formula that involves gases and a constant. And so R shows up in like all sorts of crazy places in science. Now, the units of the gas constant are dumb. The units are liter atmospheres per mole Kelvin. What does that mean? And the answer is it doesn't mean anything. Constants are there so that you can use them to cancel out units. They themselves have no meaning. They're just a ratio. So don't worry about trying to conceptualize what is a liter atmosphere mole Kelvin? Because it's not a thing. It's a model. All right. Now, the issue that's going to come up is that I'm going to give you gas law problems, and that's what we're going to do for the rest of the period, pretty much. And I'm not going to give you any context on which formula you need to use. Should you use the combined gas law, one of the individual gas laws, or should you use the ideal gas law? By the individuals, I mean Boyle or Charles' law. And really, it only comes down to either the combined gas law or the ideal gas law. Because in the combined gas law, you could just ignore anything that you don't have information for, and it'll solve. So, if you were only given pressure and volume, you could use the combined gas law and just cross out the temperatures, because they're the same, right? If the temperature isn't listed, it didn't change. All right. So here's an example of the ideal gas law in action. We're going to do this one together. I have a balloon that contains helium. The mention of the helium is actually relevant here. We'll see why. I'm going to heat it to 425 Kelvin at a pressure of 1 atm. And then I measure the volume, and the volume is 0.925 liters. How many grams of helium are in the balloon? All right, so let's write out what all these things mean. All right. And R is a constant. I just didn't want to label it. All right. Of these four variables that we can measure, which one of you could tell you the mass? Now, none of them are mass, but one of them is close to mass if you remember stuff from Chapter 6. Which unit might that be? I realize some people may have rewound the video and are watching backwards, so think about which variable it could be. And hopefully you've picked this variable. Because remember, you can turn moles of something into grams of something if you know what it is, right? And hey, the problem did say helium. So let's solve for n here. So if I solve for n, that would be this, PV divided by RT. Because I divide both sides by RT, yeah? And so according to our problem, that would be 1 atm. The volume would be 0.925 liters. The ideal gas constant is a constant, and we can look that up. And then the temperature was 425 Kelvin. Now, as long as all of our units match, we can start canceling them out. So if you put your temperature in Celsius, you can't cancel Celsius and Kelvin. Then that's the same. So you have to convert it so that it matches this constant. This is the only unit that's left, so that'll be the units of my answer. And so we will enter all of that into this calculator. I typed the wrong number. And so I got 0.0265 moles. What were they moles of? They were moles of helium. And then, if we go back to Chapter 6 stuff, we can turn moles of helium into grams of helium using the periodic table, right? So I just take this number, times it by the molar mass of helium, and there's the mass of helium. So we can use the ideal gas law to get any variable out of that we want. Pressure in atmospheres, volume in liters, number of particles in moles, or T in temperature. Or temperature in Kelvin, sorry. If we're solving for moles, we can then use moles to do whatever we need to. So we could turn moles into grams. Excuse me. Or do anything that we did in chapter 6. All right, let's give you some problems to try. All right, here's a different problem. Now, I'm not going to tell you what type of problem it is. I'm just going to leave it on the screen and say, I'll give you 5 minutes to solve it. So good luck. 1 or 2 more minutes and we'll go over the answers. All right, let's go over the solution here. Okay, so I have a volume, a pressure, a temperature, and then I have a volume and a pressure, and I need a temperature. So just because I have duplicates, I know that I have some form of before-after. So we'll pull out the combined gas law and we'll just start filling things in. So a piston contains a gas that occupies a volume of 0.200 liters at 1 atm and 273 Kelvin. The piston is compressed to a volume of 0.0950 liters at 2.75 atm. What will the temperature of the gas be after the compression? So the act of doing this compression changes the temperature because we've squished all the molecules into a smaller volume. And they have some pressure, so they must have some temperature to them too. Whatever that temperature is, we're going to solve for it. So we're going to solve for T2, which means T2's got to go back up to the top, so we're going to multiply both sides by T2. And then I need to get rid of all this other stuff, right? So I'm going to multiply by T1 and divide by P1V1. And that would give me T2 equals a bunch of stuff. So we're going to input all of that stuff because that's what T2 is. So P2, oops, it scrolled off the screen for you. P2 was 2.75 atm. V2 was 0.0950 atm. Oh, sorry, not atm. That was liters. And then T1 was 273 Kelvin. And then we'll divide by P1, which is 1 atm. And then 0.200 liters, which is V1. And then all of our units cancel out except for Kelvin, which is what our answer should be in. So let's see what we get. And then divided by 1 times 0.2. 357 Kelvin. All right, excellent. All right, I got another one for you. We'll put this on the screen here. This will be the last one that we do because this is all the time that we have. So again, here, oops, I just showed you the answer. Actually, this problem is exactly the same as what we just did, so this is the one that I was supposed to show you so that I could get the what's it called? Canada Lego GoPro video, the weather balloon. That's what I wanted to do. All right, so I'm gonna put these on the screen here. I don't really have time to solve any of these, really. So what I'm gonna do is I'm gonna just pick the second one here. I'm gonna do this one for you because we only have 6 minutes, so I'd give you like 1 minute to do it. That's not enough time anyway. So we're gonna do this second problem. Because it uses the ideal gas law, and it's just a separate application that we can use it for. Because instead of counting the number of moles, we can count the number of molecules that are in there. All right, so I have a volume, a temperature, and a pressure, and I want to know the number of molecules of helium. Now, remember that when you know the number of moles, you can turn that into particles. In other words, this is molecules, or grams. So if a problem asks you to solve for either the number of molecules, particles, whatever, or the number of grams, you automatically know that you need to know the number of moles. And therefore, you should use the ideal gas law. Because that's the only one that can input any of those units. So if I need to know the number of molecules, I need to solve for n. And so now I just take all the numbers out of the problem. So pressure would be 1 atm. The volume would be whatever it says, 0.420 liters. R is the gas constant, which we can look up. And T is the temperature, which is 302 Kelvin. Kelvin goes away, atmospheres goes away, liters goes away. So we got molecules here, so that means we got moles. 1 times 0.420 divided by parentheses 0.08206 times 302. So I have this many moles of helium. And then, if I want to know how many molecules of helium, which is actually just atoms, how many atoms are in a mole, regardless of how many or what it is? Well, it's Avogadro's number, right? So I just take our number that we got here and we multiply by Avogadro's number. Oh, for fuck's sake. There we go. There you go. All right, so we've done enough gas law problems that you've seen pretty much every type of problem that I could give you. So when I put the homework practice back up here, make sure that you do as many of those problems as you can. Because this is really just the meat and potatoes of the math that we're going to do in Chapter 7. All right. When we come back on Tuesday next week, we're going to finish Chapter 7. We're going to talk about phase changes. We're going to talk about intermolecular forces, which are super important for biology. And we might even start Chapter 8. So we are getting close to the end of the content. Like, we're very close to the end of the quarter, right? Next week is week 8. There's only 8 weeks, 8, 9, and 10 left. And then finals week. So make sure you're staying on top of the work. Lab worksheet number 3 is closing tonight, so get that in by the deadline. Quiz number 6 is due next week. And we're going to continue talking about Chapter 7 on Tuesday. So I do want to thank everyone for coming to the lecture. If you have any questions, again, make sure you let me know in the Discord. Happy to help you there. Send me an email. Let me know what I can do. All right, go out and enjoy the sun. Take care.